Dear learners, welcome to the course Electromagnetic Fields. In this video, I will explain electromagnetic model. Before starting the electromagnetic model, we shall discuss what is meant by model. A model means a mathematical representation of a series of measurements, experiments, observations, assumptions, approximations and simplifications. Then, what is electromagnetic model? Electromagnetic model is a mathematical representation of electromagnetic fields or phenomena. Electromagnetic modeling is the process of formulating the interaction of electromagnetic fields with physical objects and the environment. It explains the fundamental concepts of the electromagnetic field. It is the outcome of number of calculations, observations, experiments and simplifications. The electric and magnetic fields are the basic quantities of nature. Hence, obtaining electromagnetic model of such fields plays an important role in the study and analysis of various electromagnetic fields and related phenomena. Generally, there are two approaches used to develop electromagnetic model: inductive approach and deductive approach. We will discuss about one by one. Let's see what is inductive approach. Inductive approach. Using the inductive approach, one follows the historical development of the subject, starting with the observations of some simple experiments and inferring from them laws and the theorem. It is a process of reasoning from particular phenomena to general principles. Another approach is deductive approach. Deductive approach, on the other hand, postulates a few fundamental relations for an idealized model. The postulated relations are axioms from which particular laws and theorems can be derived. This approach is otherwise called as axiomatic approach. The idealized model we adopt for studying a scientific subject must relate to real world situations and able to explain physical phenomena. Otherwise, we would be engaged in mental exercises for no purpose. Three essential steps are involved in building a theory on an idealized model. First, some basic quantities to the subject of study are defined. This is the first step, defining the basic quantities of electromagnetics. Second step is rules of operation. Here, the rules of operation of these quantities are specified. Third, some fundamental relations are postulated. These postulates or laws are invariably based on numerous experimental observations occurred under controlled conditions and synthesized by brilliant minds. We consider one familiar example is the circuit theory built on a circuit model of idealized sources and pure resistance, inductance and capacitances. In this case, the basic quantities are voltages, currents, resistances, inductances and capacitances. The rules of operations are those of algebra, ordinary differential equations and Laplace transformation. And the fundamental postulates are Kirchhoff's voltage law and current law. In a like manner, the electromagnetic theory can be built on a suitably chosen electromagnetic model. So, in this video, we shall take the first step of defining the basic quantities of electromagnetics. The second step, the rules of operation, encompasses vector algebra, vector calculus and partial differential equations. The fundamental of vector algebra and vector calculus will be discussed in another video. The third step, the fundamental postulates, will be presented in forthcoming videos. The quantities in our electromagnetic model can be divided into two categories such as source quantities and field quantities. We know that the source of an electromagnetic field is invariably electric charges at rest or in motion. Here I have listed the source quantities. Here electric charge is represented as Q or capital letter Q. It denotes electric charge. Electric charge is a fundamental property of matter and exists only positive or negative integral multiples of the charge on an electron. We know that charge electron is equal to 1.60 into 10 power minus 19 coulombs, where C is the abbreviation of the unit of charge, coulombs. The principle of conservation of electric charge, like the principle of conservation of momentum, is a fundamental postulate or law of physics. It states that the electric charge is conserved, that is, it can neither be created nor be destroyed. This is the law of nature and cannot be derived from other principles or relations. Electric charges can move from one place to another, and it can be redistributed under the influence of electromagnetic field, but the algebraic sum of the positive and negative charges in a closed or isolated system remain unchanged. The principle of conservation of electric charge must be satisfied at all times and under any circumstances. We define a volume charge density rho v as a source quantity. Rho v is equal to limit del v tends to 0 del q by del v, charge per unit volume. Unit is coulomb per meter cube, where del q is the amount of charge in a very small volume del v. In some physical situations, an amount of charge del q may be identified with an element of surface del s or an element of line del L. In such cases, it will be more appropriate to define a surface charge density rho s or line charge density rho L. Rho s is equal to limit del s tends to 0 del q by del s, charge per unit surface. Unit for rho s is coulomb per meter square. Similarly, rho L is equal to limit del L tends to 0 del q by del L, unit is coulomb per meter. And the next quantity is current. Current is the rate of change of charge with respect to time, that is I is equal to dq by dt, unit is ampere, where I itself may be time dependent. The unit of current is coulomb per second or amperes. A current must flow through a finite area, a conducting wire of a finite cross section. Hence, it is not a point function. In electromagnetics, we define vector point function volume current density or simply current density J vector, which measures the amount of current flowing through a area normal to the direction of current flow. Current density is J vector. Unit is ampere per meter square. For very good conductors, high frequency alternating currents are confined in the surface layer as a current sheet instead of flowing throughout the interior of the conductor. In such cases, there is a need to define a surface current density Js, which is the current per unit width on the conducting surface normal to the direction of current flow and has the unit of ampere per meter. Next we move on to the field quantities. There are four fundamental field quantities in electromagnetic: electric field intensity, electric flux density, magnetic flux density, magnetic field intensity. These quantities are listed here with the symbols and their unit. Electric field intensity is represented as E vector. Here vector is represented in boldface letter. So electric field intensity is E vector, unit is volt per meter. For electric flux density, D vector, unit is coulomb per meter square. Similarly, magnetic flux density is B vector, unit is Tesla or Weber per meter square. Another quantity is magnetic field intensity, H vector, ampere per meter. Electric flux density is related to the electric field intensity by permittivity of the medium. D vector is equal to epsilon naught E vector. Similarly, H vector is equal to 1 by mu naught B vector. Otherwise, B vector is equal to mu naught H vector for free space. I hope you would understand electromagnetic model. Thank you.